as accurate as needed, as fast as possible, new VirtualLab Fusion 2023.2. This is a title that we have decided to give to this release webinar. Before I go on to listing all the new features, all the novelties of VirtualLab Fusion 2023.2, I want to explain the first part of that title a little bit more. Also, give a bit of an introduction in case there are any among you who have no idea what Lightrance is, what VirtualLab Fusion is, give a bit of context to make sure that we're all starting from pretty solid ground here. So that's where I'm going to start, from this slide, where at the bottom left corner we can see the company Swarovski Photonics. That is a company responsible for the development of the optical modeling and design software VirtualLab Fusion, which we have on the right of the slide there. Based on this software product and the underlying theory and technology, we have the work that Lightrance does. Lightrance is a general distributor of this optical modeling and design software VirtualLab Fusion. We work with a wonderful team of distributors around the world, and we also do other things. We organize dissemination events like this webinar, also courses in the use of the software both online and on-site. We offer technical support for users of the software of VirtualLab Fusion, and we also offer consulting services in the field of optical engineering, once again based on the VirtualLab Fusion software and the underlying theory and technology. But why do we use the tagline "as accurate as needed, as fast as possible" when talking about VirtualLab Fusion software? Whenever simulation technology is part of the conversation, there is going to be a compromise between the accuracy of the results that simulation is going to deliver and the speed with which the simulation is going to deliver those results. Having control of this accuracy-speed balance is a key part of simulation technology. And the way that this control is achieved is through a pool of interoperable modeling techniques, which, in the case of VirtualLab Fusion, happens on a single platform. So this interoperability of modeling techniques is not just something that we talk about, it has become quite a tendency in the field, but something that is exclusive to the VirtualLab Fusion software is the fact that everything happens on a single software platform. This has several advantages. We use a consistent mathematical model throughout the simulation, which means no information is lost, changing from one model in one piece of software to a different model in another piece of software, and then trying to connect them together. Because that connection is done in the platform itself, is part of the engine itself, that model is consistent, no information is lost. It's also a lot more user-friendly, a lot more convenient, particularly when we talk about non-sequential systems. Think, for example, augmented reality glasses and the simulation of that optical device. In that case, if we had to manually apply a modeling technique for the different parts of a system and then make that non-sequential connection manually, that would become a very, very cumbersome process. So with this single platform interoperability, we have the benefits of that consistent model, which means we do not lose information in the process of changing, for example, from rays to fields and back. There is a whole theory keeping that model consistent underneath. And also it adds convenience, it adds ease of use, because that non-sequentiality is intrinsically included in that single software platform. So this is a bit of an introduction to the software for those of you who maybe are not familiar with it. And now let's talk about what is new in this latest version, 2023.2. First of all, this is not very technical, but I want to get it out of the way at the beginning. We have a completely new license model. Those of you who have been with us for a while will recognize perhaps a certain going back to basics, rather than having as for previous version 2023.1, having two versions of VirtualLab Fusion, basic and advanced, and then different toolboxes, many of them in two versions, silver and gold, which was hard to keep track of, we have simplified the whole license model, and the current structure is a single software platform, VirtualLab Fusion, that is a starting point for everything. And then on top of that, we can add additional packages depending on what the application we have in mind for the software is. Among them, the grading package. You can read all of the available packages there on screen. And at the end of that list, which is just a screenshot of our website, of the part that explains this license model, we have that new distributed computing package, which is the next part that I'm going to talk about, and it's one of the stars, if not the star, of this latest release. This is a new package, the distributed computing package, that is a game changer when it comes to complex simulations, or the simulation of complex systems that are composed of many individual elementary simulations that are decoupled from each other. So just to give some examples, and we're going to see this applied later on in the presentation. For example, in, again, the same example I mentioned before, augmented reality glasses. In that situation, we normally have to perform a simulation for a field of view. That means a range of incident directions. Each of these directions will propagate through the system independently. There will be there's no coupling, no entanglement between them, which means we can perform the individual simulations as standalone simulations and then combine the results together in order to get to characterize a response of the system for that whole field of view of interest. In this case, where we can decompose that very complex simulation into a set of individual elementary simulation tasks, this is where the distributed computing package really shines. What this does is it's going to allow you to set up that set of elementary simulations on your computer and then distribute the individual elementary simulation tasks among different machines in your network so that you can fully parallelize the calculations, those elementary simulation tasks, and drastically reduce simulation time. Again, this is game-changing technology for many, many applications. This is what it looks like, just a sneak peek, what it looks like in VirtualLab Fusion. This is the VirtualLab Fusion user interface, and you would start your server from the machine that you're using to control the whole simulation process. We have a dedicated distributed computing tab right there. And then you can select the different machines that are connected to your network and start multiple clients on each of those machines. Then the elementary simulation tasks will be distributed among those machines in your network, and the calculations will be done in parallel, which is the key aspect here, that parallelization of the different tasks. This is independent from the multi-threading management, which was already part of the software and which incidentally has also been improved for version 2023.2. Let's look at some actual practical examples of this new distributed computing tool being applied. The first instance is a microson interferometer, where the source has a white light spectrum. And we're going to be seeing diffraction effects in this interferometer. This is what the system looks like. So a well-known microson setup. And the key to the distributed computing side of things here is the spectrum, the wavelength spectrum of that source. We're going to be using a point source that has a wavelength spectrum that covers the range between 400 nanometers and 800 nanometers. And we need, in order to sample that spectrum well, we need 500 steps. That means 500 individual wavelengths. And for each of these wavelengths, the simulation of the system has to be performed, and then the results combined together at the end in order to be able to visualize the whole effect, the actual physical result of using this system with that source. If we go through the system here, we see that the reference path, the reference arm of the interferometer has a tilted mirror. That's the component that's down from the interferometer there. That's the reference path. And then in the other arm, we have placed a reflective sample that has a relief with very sharp edges. These sharp edges are going to cause diffraction that will be visible in the detector. Just as an aside here, one of the key technologies in VirtualLab Fusion is the diffraction, the inclusion of diffraction in our simulations. There is a whole mathematical theory behind it, and the tools that we offer allow the user to switch diffraction on and off in the simulation. This is controlled through the through the Fourier transform technology that is implemented in the software. So we can choose to include diffraction here or exclude it, and we can then compare the two results with and without diffraction. That is not something that we're going to be investigating in detail here today, but you will find a link to this very setup where the comparison between the situation with diffraction and without diffraction is presented as well. So that is not something that we're going to be looking at specifically here, switching the diffraction on and off, but it's really one of the jewels in the crown of our technology, and it's worth mentioning that here. So here we are going to include diffraction throughout the example. So that is not part of the example. We're going to have diffraction switched on throughout the example in this case. We start by performing the simulation of the system for a single wavelength sample, and the simulation takes approximately 7 seconds. Of course, all these times that we mention, or these durations that we mention in the presentation here today, will depend on the specific hardware available. So they will likely change depending on the machine that you're using, but they are given here for reference. So the times that we give here are comparable with each other and against each other, but they may not be if you run the simulation on a different machine. So just for reference, just for rough illustration here, a single simulation for a single wavelength takes 7 seconds. Then, of course, if we perform all the 500 simulations for the 500 different wavelengths sequentially, one after the other, on a single machine, this is more or less, approximately, very roughly, going to add up in a linear way, which means overall the total simulation time for all those 500 simulations on a single machine without distributed computing is going to be approximately an hour, 57 minutes, as we see noted there on the slide. The combination we see, I want to point out, we see the diffraction effects there. Diffraction is once again included. We see the color effects from the dispersive nature of the setup of that interference. We see the temporal coherence properties of the source reflected in the result. We will see later the full detector window and how only for those parts where the path length, the optical path length of the two arms of the interferometer is exactly the same, only then do we get full interference. But because we have a partially temporally a source with partial temporal coherence, where those where the optical path is different for both arms of the interferometer, the appearance of interference is lost. So we have a fully accurate simulation of a realistic physical experiment. Now, if we apply distributed computing here, the result is the same. The only thing we're doing is, instead of calculating all those 500 individual simulations on a single machine, just making use of, again, the multi-threading capabilities intrinsic to the software. If instead of that, we use a new distributed computing software package, to distribute the elementary tasks among different machines in a network, we see a little bit what that would look like. We use 24 different clients instead of almost an hour of simulation time. We decrease that to 3 minutes and 50 seconds, just below 4 minutes. A comparison here of the times, and once again, I want to highlight that very accurate simulation of the temporal coherence of the source and the chromatic effects that come from the dispersive nature of the system. And of course, the main point to highlight here is the effect, the advantage, the drastic advantage that is provided by the distributed computing package in situations like this one, where we have many elementary simulation tasks to go through for the simulation of the entire system. Another example of the potential of distributed computing is, as I already mentioned, augmented reality devices. Here we have a setup like the one you see on screen. We have a 1D EPE type layout. This would be the device for one eye, so we would have a symmetric situation for the other eye, but it's enough to perform the analysis just for one half of the device. The other half is completely equivalent. We have real gratings for the in-coupler, the expander, and the out-coupling. Those gratings have a binary profile, but in the case of the expander and the out-coupler, we apply smooth variation of in this case, the fill factor of that binary grating. What we want to do is analyze we're going to use a test image, a checkerboard test pattern, to analyze the performance of this device, of this setup. A single simulation will take about 8 seconds. As was noted on that initial slide. Here we see that checkerboard pattern. We resolve this test image with 101 pixels 101 times 101 pixels to sample that whole field of view of interest, 36 degrees times 24 degrees. That means we have 101 times 101 elementary simulation tasks in this simulation, in this complex analysis. That amounts to a total of 10,201 elementary simulation tasks. If we use a single machine to perform those simulations, the total time runs up to over 31 hours. If we use 35 clients with that distributed computing package, the simulation time is reduced to a little bit over an hour, as we can see on the slide there. And once again, we can see a comparison on this slide of that drastic reduction in calculation time that can be achieved using the new distributed computing package for this application. Next up, we have the parameter variation analyzer, and we stay with the topic of multiplexing, of multiple configurations of optical systems, a little bit in the same vein as we also discussed with the distributed computing package, because the parameter variation analyzer allows us to calculate merit functions on the basis of multiple configurations of a single system. For those of you who were familiar with VirtualLab Fusion software before version 2023.2, you will already know the parameter run, which is a tool that allows us to perform parameter sweeps with our optical systems to investigate how the results change when we vary a given parameter or a given set of parameters in our system. The parameter variation analyzer builds on that. It has an internal parameter run, which you can configure as usual, what parameters you want to vary, the range of variation that you want to allow, and how many iterations you want to use. And then the novelty is that on top of that, you have the option of using programming. C# is the language that we use in VirtualLab Fusion, in order to take those results from your parameter run and calculate additional merit functions on the basis of all those results, in order, again, to have going in the direction of multiplexing of multiple configurations of a system. Let's take a look at one example of the parameter variation analyzer at work. And here we're going to optimize a slanted grating for robustness. Let's take a look at the system. This is what our slanted grating is going to look like. We're going to be using a green wavelength, 532 nanometers, linearly polarized light. Those are the characteristics of the source here. The working order that we're going to be optimizing for is the first order in transmission. We have different values of the fill factor listed there, and then the optimization parameters afterwards are going to be the grating height and the period of our slanted grating. On the right of that slide, we can read that what we want, the first task here, is to perform a robustness analysis. So we're going to be looking at the efficiencies produced with two different fill factors ranging between 49% and 51%. And we're going to combine these results in two different merit functions that we can then use for that robustness analysis: uniformity contrast and the mean efficiency. The first tool, and this is again a reminder, this is not new, the first tool that we're going to be using for the analysis is the grating order analyzer, which provides information about the diffraction orders and how the field is distributed among the different diffraction orders of a grating, of a periodic structure. On top of that, using the grating order analyzer to produce the results, we use the parameter variation analyzer, where we configure the variation of the fill factor. We see right there marked that range from 49% to 51% fill factor in 5 different steps with a step size of 0.5%. And we calculate, using programming, the merit functions of interest, which are mean efficiency, that we want to maximize, and uniformity contrast, which we want to minimize. And eta in those formulas denotes the efficiency for the first order in transmission for a given fill factor. So we're exclusively looking at that first order in transmission, the working order. We use the parameter variation analyzer to calculate that mean efficiency and the uniformity contrast, and then on top of that, we can then use the inbuilt parametric optimization tool to optimize our grating using those two merit functions. We want to maximize, again, the mean efficiency, and we want to minimize the uniformity contrast. So we set the parametric optimization accordingly, we configure it accordingly, and let the optimization run. In practical terms, we're going to see that there will be a certain trade-off between the mean efficiency and the uniformity. So knowing this, the user, the optical designer, can choose what he would prefer to favor and perform the optimization in that way. You can adjust the weights in the optimization and adjust the trade-off and which one of the two merit functions you would want to favor in your particular optimization. So this very nicely illustrates a potential workflow using the new parameter variation analyzer and how the different tools build on top of one another. We started from the grating order analyzer to produce the results for each value of the fill factor. Then with a parameter variation analyzer, we calculate the global merit functions for the whole range of interest of that fill factor. And then on top of that, using the merit functions calculated with a parameter variation analyzer, we can perform an optimization of the device. Those would be the two highlights, so to speak, of the new version of 2023.1. But now I want to mention a couple of additional new things and novelties, improvements, updates quickly before we finish. Again, this is not going to be an exhaustive list of everything that is new. You will find a link to the release notes later on. Next is the Field Insight Component Analyzer FMM. This already existed. This is not a new tool, but it has been updated to include 3D results. It means now it works as well for 2D periodic gratings. Previously, it worked exclusively like this. You would look at a 1D periodic or lamellar grating, and you would be able to look at the cross-section of the different components of the electromagnetic field inside your grating, inside your micro or nanostructure. The update now with version 2023.2 allows us to look at a full 2D picture of the 2D periodic grating, which of course, when we have 2D periodic structures, is fundamental as well. And in this case, it provides us with a different it slices that Z direction of modulation of the structure. So this is another very exciting update. And then let's do it a bit more quick fire style now towards the end. The 3D system view has also been updated. Again, not a new feature this time, but an update. We have a magnifying glass, and I think a really cool addition is that we can now measure distances in the 3D view. You see it right there on the slide to the right, the screenshot on the right. You see a red arrow that has been put there by a user, and the number also in red tells you the length of that line and also the projections in the given plane in X and Y. This is only available when the full ruler is activated. But this is, I think, a very practical addition in this latest version. And once again, there are a lot of very exciting novelties, improvements, updates, but we don't have the time to go exhaustively through all of them here. So again, you can find that is an active link right there to the release notes of version 2023.2. Do go and read them if you're interested in all the details. I hope you found this presentation interesting. I hope you find these new features as exciting as we do. And now we can open the floor for questions, and we can do that Q&A. Thank you for listening.